This one goes out to all my sports friends out there. Drew Bledsoe throws a football with an initial speed of 100 feet per second. That's my initial speed, VO. At an angle of 35 degrees, so theta equals 35 degrees. The ball leaves Drew's hand at a height of 6 feet, so h equals 6. We are also given some equations to help us with this, where we are defining x as the initial velocity times cosine theta times t, and y equals negative 1/2 g times t squared plus the initial velocity times the sine of theta t plus h. Now remember, x is our horizontal measure, or side to side, and y is our vertical. So that'll come in handy to remember those definitions in a little bit. The next thing that we are asked to do, or the first thing we're asked to do in A, is to find the parametric equations that describe the position of the ball as a function of time. We already really have these in function of time. We just need to simplify them. So for x, I can plug in 100 for my initial velocity, cosine of 35 degrees times t. If I plug that into my calculator, I get 81.9 t is equal to x. For the vertical equation, I also need the piece of information that gravity is 32 feet per second, or 9.8 meters per second. I need to look at the units I've been given. I've been given feet per second, so I'm going to go ahead and use this 32. So I can plug in y equals negative 1/2, plug in 32 for g times t squared, plus VO, 100, sine theta is 35, t, and plug in 6 for my height. So simplifying, I get y is equal to negative 16 t squared plus, I'm just going to use my calculator and get 57.4 as 100 sine 35 t plus 6. So these are my parametric equations that describe the position of the ball as a function of time. Again, this is the up and down position of the ball over time, or sorry, that one. X is my side to side position over time, and Y is my up and down position over time. Problem B is asking how long the ball is in the air. Well, thinking about this, the ball goes up into the air and then ends up hitting the ground, at which time it's no longer in the air. So there's some key information there that's implied but not very clear, and that is that we are at a height of 0. That means our y equals 0 at height 0. So you have a couple of options here. You can substitute 0 into this original equation. 0 equals negative 16 t squared plus 57.4 t plus 6, and solve that. That would be the quadratic formula, and I'm thinking you're thinking, ew. I would be thinking, ew. So what I'm going to go ahead and do is I'm going to take this equation here and plug it into y1 in my calculator using x for t. And then I'm going to set my window, and I'm just going to guess and check that as a negative 10 to 10 and hit zoom 0. When I do that, my graph is kind of zoomed out, so I'm going to end up with a second guess and check with my window of like negative 3 to 5 for my x min and max, and click zoom 0. That gives me an okay window there, and what I'm really looking for is this point here where I'm crossing the x-axis So that's a 0. So this is where we can do second, trace, 0, set a left bound, set a right bound. You can just hit enter through the guess. And what your calculator is going to do is it's going to tell you that when x equals 3.66 something or another, y equals around 0. So that means, remember, x is really t for a calculator. When t equals 3.7 seconds, our ball is no longer in the air, it's on the ground, so the ball is in the air for 3.7 seconds. 11C is asking us when the ball is at its maximum height. Again, we're going to keep that same equation in our calculator because that's the equation of the up and down. It's the vertical equation for the position of the ball. And what we're looking for is the maximum. So the x value that it gives us when we do second, trace, max, get your left bound and your right bound and just hit enter through the guess. It's going to give us an x of about 1.8 seconds and a y of about 56.8. So remember, the x is our time. So at 1.8 seconds, the ball is 56.8 feet in the air, which is our maximum height. And then the last thing is 11D. And this is asking us to determine the distance the ball traveled. And when it's saying distance, it wants the horizontal displacement, which we have defined as x. So we need to go back to our equation for x, where x equals 81.9 t. And for this, we need to know how long the ball is in the air time-wise, which we already determined was 3.7 seconds from problem 11b. So we can plug in 3.7 for t, and solving, we end up getting 299.8 approximately feet from the start where Drew Bledsoe left it to where the ball landed on the ground in horizontal displacement.